Let us see about laminar flow through pipes in this video. First, we need to differentiate between laminar flow and turbulent flow. We have seen that to describe laminar or turbulent flow, we need Reynolds number. If the Reynolds number is less than 2000, that is called as laminar flow. If Reynolds number is less than 4000, called as turbulent flow. This is for pipes. Flow through pipes, then these Reynolds number values are valid for laminar and turbulent flow. If Reynolds number lies between 2000 and 4000, that is called as transition flow. So these all we have seen in the last video. In this video, let us see about laminar flow. So the main factors that we need to analyze is velocity, and first parameter is velocity and other is shear stress. So we need to analyze these both factors in this laminar flow. First, let us understand how the velocity will be present in the fluid. So if the fluid is traveling in this direction, the velocity will not be same at all the points. Here the velocity will be different, here the velocity is different, here another velocity, here another, here another, here another. So we have seen that there is here there will be no velocity, and here at the center there is maximum velocity, and here there will be some less velocity, here some more, and here some more. The velocity distribution will be in this way. So if we join all these points, it looks like this. So the velocity at the wall surface will be 0, and that is called as no slip condition. So that is no slip condition. This is because the fluid particles are attached to this this wall surface, as the friction will be present. So the fluid particles will be attached to that, and there will be no velocity of the fluid particles at the wall. So as the particles that we are considering move away from the wall, there will be increasing velocity, and at the center that will be the maximum velocity. So that will be the velocity distribution. What about the shear stress? The shear stress will be here. The shear stress will be more because there is a friction present and the velocity is 0. So the maximum shear stress will be present here, and the minimum will be 0 at the center. This is the center. The minimum shear stress will be present, and from on downside also the maximum shear stress will be at wall. So this is the shear stress distribution, and this is the velocity distribution. Now let us understand this laminar flow. So how does the laminar flow develops into a fully developed flow? If you see here, while entering the pipe, the velocity will be uniform. So there is uniform velocity, and as it goes inside the pipe, the velocity at the wall will be less, and mostly that will total velocity profile will be uniform, but at the wall the velocity decreases. And this as it goes deeper, as it goes inside the pipe, the velocity profile changes continuously, and finally it reaches the velocity profile that we have discussed this one. So At that point, the hydrodynamic entrance region ends. So from entry of the fluid to the velocity profile that we are discussed, to that velocity profile, if the fluid reaches, that region is called as hydrodynamic entrance region, and that pipe length is called as hydrodynamic entrance length. Hydrodynamic entrance length. So after this, the velocity profile will remain same. So this velocity profile will remain same along the pipe. So same velocity profile will be remaining. But in the hydrodynamic entrance region, the velocity profile constantly changes to the velocity profile that we are discussing now. So that will be the hydrodynamic entrance region. And this is the hydrodynamically fully developed region. So what is hydrodynamically fully developed region? That is, the velocity profile remains constant throughout the pipe. That is called as hydrodynamically fully developed region. So we need to mention some parameters here. Velocity boundary layer. This is called as velocity boundary layer, where the shear forces are effective. So where will be the shear forces effective? Shear forces will be effective near the wall surface. So here the shear forces will be effective. So that is called as velocity boundary layer. So what is developing velocity profile? This is the actual velocity profile, fully developed flows velocity profile. But this one, so these are all developing velocity profile. So this is fully developed velocity profile. This one is fully developed. This one is fully developed. And there is a region. So this one, this. So this all region is velocity boundary layer. This all region is velocity boundary layer region. And this is called as this blue color one. That is called as velocity boundary layer surface. Velocity boundary layer surface. That divides this velocity boundary layer and irrotational flow region. This is called as irrotational flow region. So this one is called as irrotational flow region. So now let us find out what is the shear stress. Let me draw. So this is the pipe length and this is center. Consider elementary fluid element. So the pressure will be acting, and here the pressure will be P plus dou P by dou X into dx, if this is dx. So what are the other forces that will be acting? Shear stress will be acting. So shear stress will be opposite to the flow. If I consider the flow is this side, shear stress will be opposite. So what will be the force balances? So one, considering this side as positive and this is negative. So P into pressure into area. This area, what is this area? This is radius r. So pi r square, and this is minus P plus dou P by dou X into dx into area is same pi r square minus tau. Tau is also minus tau into, so what is the surface area? Surface area of that element. So 2 pi r into dx. 2 pi r is the perimeter into dx gives us the surface area, which will be equal to 0. So p into pi r square minus p into pi r square minus dou p by dou x dx into pi r square minus tau into 2 pi r dx is equal to 0. So here p into pi r square gets cancelled. Minus dou p by dou x dx into pi r square is equal to, taking this shear force that side, tau into 2 pi r into dx. dx gets cancelled, and pi 1 r gets cancelled. The remaining is tau is equal to minus dou p by dou x into r by 2. So this is the shear stress at any point. So that will be the shear stress. So where will be the maximum shear stress? Maximum shear stress will be at tau max. Here, how is the shear stress distribution? This is shear stress distribution. So the maximum shear stress is at the wall surface. So tau max is equal to tau naught. Sometimes we represent it with tau naught, which is equal to tau wall, which is equal to minus dou p by dou x into r by 2. So this minus is indicating that the shear stress acts in a direction opposite to the flow of the fluid. So we have found the shear stress. Now let us find the velocity. So there was a velocity profile. So from this this tau max will be constant. So if this is tau max is constant, then minus dou p by dou x should also be constant. Since r by 2 is constant, minus dou p by dou x should also be constant. And let us find the velocity now. So velocity at any point. From center, it is at r distance, and from wall surface it is at distance y. So r plus y is equal to capital R. Capital R is radius of the pipe. So capital R is radius of the pipe. Differentiating this, we get dr plus dy is equal to, differentiation of a constant is 0. So dr is equal to minus dy. Okay. Now tau is equal to minus dou p by dou x into r by 2. But we also know that tau is equal to mu into du by dy. So tau is equal to mu into du by dy. And now minus dou p by dou x into r by 2 is equal to mu into du by, so what is dy? Dy is equal to minus dr. So keeping minus here, dr. So minus gets cancelled here. Dou p by dou x into r by 2 is equal to mu into du by dr. So now taking this to the side, so du is equal to 1 by 2 mu into dou p by dou x into r dr. Now integrating both sides, integral du is equal to, taking constants outside, 1 by 2 mu. Dou p by dou x is a constant. We have seen in the shear stress, dou p by dou x is a constant. Integral r dr. So u, differentiation of a constant, differentiation of 1 is u, 1 by 2 mu dou p by dou x into differentiation of this was integration of r is r square by 2 plus some constant. So in order to find the arbitrary constant, we need to apply the boundary conditions. So how was the velocity? Velocity profile was in this way. So velocity profile was in this way, and the maximum velocity is at center. Center means r is equal to 0. So at r is equal to 0, at r is equal to capital R, at wall the velocity was 0. So at r is equal to capital R, u is equal to 0. So u is equal to 0, 1 by 2 mu dou p by dou x into capital R square by 2 plus constant. From this, c is equal to minus 1 by 2 mu dou p by dou x into r square by 2. So now substituting this value in this, u is equal to 1 by 2 mu dou p by dou x into r small r square by 2 minus 1 by 2 mu dou p by dou x into capital R square by 2. So I am taking out this common, 1 by 4 mu into dou p by dou x. I am taking minus outside, so this gives us r square, capital R square minus small r square. This is the equation of velocity profile, and this is parabolic velocity distribution. So there is square, so it is a parabolic velocity distribution. So we have got the velocity profile. So what will be the maximum velocity? At r is equal to 0, u is equal to maximum. So velocity will be maximum, or I'll write it u max. U max will be minus 1 by 4 mu dou p by dou x. Keeping r is small r is equal to 0, we will get capital R square. So there is an important relation, u by u max. U by u max. If you divide u with the u max, that will give us 1 minus small r square divided by capital R square. So this is another important one. And what about the average velocity? What about average velocity? In order to find average velocity, we can take help of discharge. So what is discharge? Discharge is equal to cross-sectional area into average velocity. This is the discharge. But also we can find that in another way. So integration of u dAc, this also gives us discharge. That is because so this is the pipe, and if I consider a fluid element, so that will be summation of all these discharges. So the fluid will be flowing from this, and summation of all these discharges give us total discharge. Now, so AC into V average and integral u dAc. So u, integral of What is U? Velocity profile. Minus 1 by 4 mu dou P by dou X into capital R square minus small r square dAc is equal to AC into V average. Now, taking constants outside, minus 1 by 4 mu dou P by dou X. So, integration of capital R square minus small r square dAc. What is differential area? So, if this is, I'm projecting this will be the area, differential area. This is radius r. Let me draw another. So this is radius r and this small length is dr. So what will be the area? 2 pi r into dr. That is equal to AC into V average. So minus 1 by 4 mu dou P by dou X. So integration of r square 2 pi r dr. So taking 2 pi r square, 2 pi r square and r dr gives us r square by 2 minus 2 pi into r cube dr. So r power 4 by 4 is equal to AC into V average minus 1 by 4 mu dou P by dou X. From where to where we need to integrate? From center to wall. So center means r is equal to 0. From up to wall means r is equal to capital R. So 2 pi r square into capital R square by 2 minus 2 pi into capital R power 4 by 4. If you put 0, the total value will be 0. So AC into V average. Now minus 1 by 4 mu dou P by dou X into 2 gets cancelled, 2. So pi into r power 4 minus pi by 2 into r power 4, that will be pi r power 4 by 2, that is equal to AC into V average. Now minus 1 by 4 mu dou P by dou X into r square into pi r square divided by 2. So I am writing this in this way. So AC into V average. So from this we can see that this is the velocity profile. This is, that is not the velocity profile, that is the maximum velocity. So maximum velocity, this is the cross-sectional area. Pi r square is the cross-sectional area. So U max by 2 into cross-sectional area is equal to cross-sectional area into V average. AC gets cancelled and V average is equal to U max by 2. So this is the relation between average velocity and the maximum velocity. And now let us see the pressure difference or head loss. There is pressure P1 and pressure P2 at this point. So the pressure is changing along the x direction. Suppose from this point I am saying it is at a distance x2, and from the same point it is at a distance x2. This is x1 and this is x2, and this length between the points is L. Now so V average is equal to U max by 2. So what is U max? Minus dou P by dou X sorry, minus 1 by 4 mu dou P by dou X into R square, which is equal to, this is U max, and which is equal to 2 into V average, 2 into V average. So now I am writing this partial differentiation to exact differential. This is because I am considering that there will be no change in the radial direction, no change in pressure in radial direction. So minus 1 by 4 mu 2 into V average. Now dP is equal to 2 into V average into 4 mu by R square, here minus dx. So that will be integrating both. So P1 to P2 here x1 to x2. Now, so P minus P, P1 to P2, 2 V average, 4 to the 8 into mu divided by R square. These are all constants, and x1 to x2. So this will be P2 minus P1, but here minus is present, so P1 minus P2, which is equal to 8 V average into mu by R square into x2 minus x1. So P1 minus P2 is equal to 8 mu V average x2 minus x1, x2 minus x1, that is L divided by R square. And if you write in D, 8 mu V average into L by D square. Sorry, this will be 32 mu VL by D square. So P1 minus P2 is equal to 32 mu VL by D square, and this V means V average. So this is valid for horizontal pipes only. Horizontal pipes and laminar, fully developed. So that is P1 minus P2. And one thing should be derived from this. We know that this is the head loss. P1 minus P2 is equal to W into HF. This is due to friction. So substituting rho G HF is equal to 32 mu VL by D square, means FLV square by 2GD. This we have seen, mu VL by D square. Now D and 1 V gets cancelled, L G. So finally F is equal to 64 by rho VD, 64 mu by rho VD. That will be F is equal to 64 by Reynolds number. This is valid for laminar flow through pipes. So this is what? This is friction factor. So this is how we got 64 by Reynolds number. Now there is another term called shear velocity. Sometimes it is convenient to represent shear stress in terms of velocity. That is called as shear velocity, and it is represented with V star. V star is equal to under root tau by rho. It is also equal to V into under root F by 8. So just remember this. It is not so important. Shear velocity represents shear stress in terms of velocity. So that is about laminar flow through pipes.